Hello and welcome to the Daily Space. I'm your host, Dr. Pamela Gay.
And I am your host, Beth Johnson.
And we're here to put science in your brain.
Welcome to February. We have survived the first month of 2022 and the 23rd month of 2020. To honor how we are all feeling of late, we're going to start the show with pretty space images.
From there, we'll look at a launch that got delayed to the point of hilarity as we kept trying to ninja stream it all weekend, finally launching on Monday.
Plus, we'll be joined by our guest, Dr. Núria Miret-Roig, at the end of the show to talk about rogue planets. We're really excited to have her here.
And we'll be back with those pretty images in just a moment. No lies. I am super glad we do a space science show because at one point in my career, I wanted to be a journalist who just covered all the news. And right now, most of the news is just not full of goodness, beauty, and light. But thanks to the Hubble Space Telescope and ExoMars Trace Gas Orbiter, we're going to fill this segment with things that are simply beautiful. First up is a set of galaxies that folks at the Space Telescope Science Institute are claiming look like a bowling ball and Starship Enterprise. Imaged as part of Julian Del Conte's and company's Interacting Galaxies survey, two of these galaxies are clearly former spiral galaxies that are interacting and are now very disturbed systems. If you tilt your head and look just right, you may even say they do look like the USS Enterprise. And yes, researchers spend more time than we should admit to saying, hey, does this look like some random object to you? The third galaxy further away is nice and round, and while there are hints of gas coming off of it, researchers remain unclear if this system is interacting with the other two, the Enterprise pair, or if it is just an innocent bystander. The research papers on this field are still in progress, and for now, all we have is an image release from NASA. But it is an image we can all enjoy, and that, like a movie preview, can get us, or at least me, excited about the full-length feature that is yet to come.
I totally buy that that is the USS Enterprise. Just as I buy that this next image looks like a tree stump, down to the rings. There are lots and lots of seemingly concentric rings, a dark outer rim, and yes, the entire image says tree stump. Except that's not a tree stump. It's a crater on Mars. This fantastic image was taken by the Cassis camera on the ESA Roscosmos ExoMars Trace Gas Orbiter spacecraft back in June of last year. It's located in a region called the Acidalia Planitia in the northern hemisphere, and just like tree rings, the rings in this crater tell the history of its creation and life. There are deposits in the middle of the crater that likely have water ice in them, and as the seasonal temperatures change, water ice undergoes expansion and contraction, causing fractures to form in the surface. Those water ice deposits were laid down much earlier in Mars's history, when the tilt of the planet's axis was greater and seasonal differences were larger. Mars's axial tilt has changed a lot over millions of years, affecting how water and ice deposits were distributed on the surface, leading to a lot of the features we see today. And today, I guess we see a tree stump.
Did I mention we spend a lot of time saying, hey, does that look like a random object to you. Seriously, we have been doing this for ages and will continue doing this as long as human beings keep being human beings. A lot of times, the names objects have were written long ago and require you to look at objects through lower power scopes that are similar to those that were used when the objects were being named. The Owl Nebula looks like an adorable little owl until you zoom in and it clearly just looks like a planetary nebula. Through a 16-inch telescope, the Tarantula Nebula looks disturbingly like there is a spider looking back at you through the eyepiece. And on first seeing it, I had to just remind myself, it's just hot gas and baby stars. Somewhere between the, it's an owl, and that's very spidery, is the chameleon cloud. Recently highlighted images from the Hubble Space Telescope don't look as much like a chameleon as the low-res images, but again, if you squint, you can see where the eye is at least. This particular nebula is reflecting toward us the blue light of young stars. The larger of these stars can be seen illuminating butterfly-shaped glows of gas. One of these objects, called a Herbig-Haro object, shines in the bottom of this image, which you can download from our website, dailyspace.org. This image was initially taken so researchers can search for brown dwarf stars. While not identified in this image, the Hubble release says that 6 of these failed stars, which are just 10 to 90 times the mass of Jupiter, were located in this image. While this may look like a single stunning image, that is just good processing. According to the image release, this 315 million pixel composite image is comprised of 23 observations made by Hubble's advanced camera for surveys. Gaps between those observations were filled by 20 wide field and planetary camera 2 images. Any remaining gaps were filled with ground-based data from ESO's Vista VirCam. A link to this massive, full-resolution image is also on our website. Sadly, we couldn't do an entire show on just pretty images, but we do have a picturesque launch to turn to next as Eric Mattis brings us the cruise ship delayed launch of the CSG-2 mission. Stay tuned.
On January 31st at 2311 UTC, after 4 previous attempts, a SpaceX Falcon 9 launched the CSG-2 mission from Slick 40 at the Cape Canaveral Space Force Station in Florida. After liftoff, the Falcon 9 headed down the Florida coast to insert the satellite into a 97.5-degree inclination sun-synchronous orbit. The twilight launch and polar trajectory led to an amazing view from ground tracking cameras at the end of first stage burn. Let's watch that stage separation.
Nico. Stage separation confirmed. And back to mission. Stage 1, boost pack startup.
And some incredible views from the ground cameras. We actually got to visually see MECO stage separation and see the first stage flip on your screen. That was incredible.
The first 3 attempts were scrubbed because of bad weather, while the 4th was scrubbed because the cruise ship entered the restricted area offshore. The usual restricted area for both planes and boats were different for this launch because of the polar trajectory, but the changed map was posted several days in advance. Because the payload was so light, only about 2 metric tons, the Falcon 9 first stage performed a return to launch site type landing at landing zone 1 about 9 minutes after launch. This is a rare type of landing since they usually land the boosters on the barge offshore, but this is the second return to launch site landing this month. The second stage coasted for about an hour before performing a second burn and then deploying the satellite into orbit. Booster 1052 is unique as Falcon 9s go, even though this is only its 3rd flight. Its first 2 launches were in 2019 as the starboard side booster on the RebSat-6 and STP-2 Falcon Heavy launches. The Falcon 9 first stages have been designed to be interchangeable between Falcon 9 first stage and Falcon Heavy side booster by switching just a few components, since the Block 5 version was introduced. However, until now, no booster has been through this process. CSG-2, or COSMO-SkyMed Second Generation Flight 2, is the second satellite of a planned constellation for the Italian government. CSG-2 is a synthetic aperture radar satellite, a type of active imaging radar used for acquiring images at all times of day, including, quote, all but the heaviest rainfall. Radar satellites work kind of like sonar, sending out their own energy and recording the reflection. Many reflections are combined to build up an image. Optical satellites, on the other hand, record light from the sun reflected off of the Earth. This quality makes radar satellites very useful for military applications, but they can also be used for agriculture and disaster monitoring, such as floods, oil spills, and wildfires. Like the first generation, CSG-2 has dual military and civilian use. CSG-2 has a number of different modes, each of which offers different resolutions and image sizes. Military users have access to a very high-resolution mode that provides images with pixels smaller than 80 by 80 centimeters, the highest resolution for civilians. The coarsest resolution has pixels that are 6 by 20 meters in size. Depending on the size of pixels, the ground coverage of an image can vary from a few kilometers on a side to large areas roughly 200 by 2,500 kilometers. The CSG constellation will be finished by 2 launches of Arianespace Vega C rockets in the next few years. Yesterday, the Center for Advancement of Science and Space, the organization that runs the science on the U.S. segment of the International Space Station, announced a new program to get students of all grade levels more access to the science conducted on the station. The program is called Expedition Space Lab and consists of a series of free lessons in 4 different areas related to research conducted on the ISS: Earth and Space Sciences, Engineering and Technology, Life Sciences, and Physical Sciences. Elementary, middle, and high school students get their own set of activities in these 4 areas. An example of one of the activities is growing a plant in the classroom and following along with the plant growing on the ISS to see the difference in how a plant develops in microgravity. Beyond the free resources, the CASES program also offers additional resources for a cost. Educators can apply for a grant to cover the cost of purchasing Expedition Space Lab resources. According to Ray Lugo, Principal Investigator and Chief Executive Officer for the ISS National Lab, quote, we seek to inspire our nation's youth and achieve great results through the implementation of Expedition Space Lab by reaching even more students, encouraging them to think about what is possible when they dream big and look up. After the break, we'll be back to interview our guest about free-floating exoplanets. Stay tuned.
Recently, we talked about a paper published in Nature where researchers detailed the discovery of at least 7 free-floating planets in a region of the Milky Way known as the Upper Scorpius OB Stellar Association. Free-floating planets are those planets that are not currently orbiting a star. We used to call them rogue planets as they had gone rogue from their solar system of origin, but since we don't know how true that particular description is, the term was changed to free-floating. Of course, since these planets are not orbiting a star, they are also not reflecting or blocking a star's light, nor are they gravitationally influencing a star's orbit. Dark, cold objects are difficult to detect. And there could be as many as 170 planets hidden within the 20 years of observations the team analyzed. Joining us now is Dr. Núria Miret-Roig, a postdoctoral researcher at the University of Vienna and the lead author of that paper I talked about that's in Nature. Thank you for joining us, Dr. Miret, and welcome.
Thank you for inviting me. It's my pleasure to be here today.
So you discovered a bunch of free-floating planets, what we used to call rogue planets. Will you walk us through the process of making this discovery?
Yes, sure. So first of all, we were interested in understanding how do stars form. And to understand how do stars form, it is a question tightly related also to how planets form, because in the end they form in the same regions together. So, and also the planets have the great advantage that they are much lighter than stars, and thus they are more sensitive to dynamical interactions and the initial conditions in the regions where stars are being formed. And that's why it's most important to identify planets and see their abundance to understand most of the process of the star and planet formation.
So I've read that there are sort of two theories on how we get free floating planets. One is that it's possible to collapse a gas cloud and actually make something big enough to be a brown dwarf, but not necessarily a star. And two, we have this possibility of them being sort of kicked out through planet-planet interaction from their previous solar systems. How do we tell the difference?
Yeah, in fact, it's very hard to know which each planet by which mechanism it formed, and this is not what we did in our study. What we did, on the contrary, is to study the general properties of the whole population. So we try to say statistically how many planets formed by each mechanism. But for the moment, we don't have the observations needed to tell by which mechanism each planet formed. But it's really good that you put this question, because it's an important point of our discovery. And the way we do the way we do this is by comparing the fraction of planets that we found in this star forming region compared to the fraction of stars, and we compare this with models that only predict that stars could be formed by core collapse, and we see that our fraction is much larger than the models what models predict, and this is what made us think that probably other mechanisms are needed to explain the large fraction of planets we found. And then what we did is also compare with models that explain how planets are formed in planetary systems and later are ejected by interactions with other planets and stars. And then by putting the two models together is the way we can explain the large fraction of planets we found.
So you looked through what, 20 years worth of observations to find all of these planets. And one of the things I noticed in both the press release and other things you're talking about is that while you've said that there are 170 you've identified, there are probably more. What leads you to think that there are more in this data set?
Well, first, we are only sensitive to objects which are 4 times the size of Jupiter or even more. And we know that there are for sure many more planets lighter than what we are able to detect, awaiting to be detected. But for that, we need larger telescopes which are able to collect more light, because planets such as our Jupiter or our own Earth are too faint to be detected at the distance of.
So this particular region that you were looking at, what made you choose it, the Upper Scorpius region?
So we chose this region because it is one of the closest star-forming regions to our home, and then its proximity makes us capable of detecting the coolest objects and the faintest, which are eventually the faintest one also. And then it's also important to detect these planets when in star-forming regions, that's to say when they are very young, because these planets are formed relatively warm, but they cool down very quickly in time. And then once they become older, it's much more difficult to identify them, because they become much fainter.
Right. So usually these are discovered using microlensing, but you guys are actually managing to sort of almost optically and visibly see them, correct?
Exactly. This was one of the key points of our discovery. And the great advantage of imaging with respect to microlensing is that afterwards our targets are suitable for follow-up studies. So that's to say, we know exactly where they are in the sky because we have observed them, and then we can do spectroscopic follow-up to study other properties such as the composition and their atmospheres, etc.
Which of course is always important because we're still trying to figure out this planetary formation thing, right?
Exactly. Yeah.
Go ahead.
No, yeah, I was about to say that I think now it's key moment to where many discoveries are ongoing. We every time know more and more planets, and this wide variety of planets is what eventually will help us to understand better their formation and origins.
So do you plan to try and catalog some more free floating planets in this region, or are you moving on to a different region in the sky now?
So we have at least two different studies ongoing now. First, we are trying to obtain a spectra, as I was mentioning, to confirm that they are indeed planets and also study their atmospheres. So first, we have this spectroscopic campaign of characterization of the planets we already found, and then for sure we will try to repeat a similar study in other regions. In this case, it will be very important to compare the fraction of planets that we find in different regions to understand how the different initial conditions in different regions affect the fraction of planets, and eventually this will give us precious information to understand the star formation process on a whole.
I, of course, I'm always excited to learn more about planetary formation. It feels like every day brings something new to the field. Is there a particular thing that you are excited about, focused on learning from these free floating planets?
Well, many things for sure, because it's a very exciting topic. But besides the 2 points that I already mentioned, like the spectroscopic follow-up to characterize their composition, and also to find many more. It would also be interesting to try, for instance, to detect if we can find disks surrounding these planets, because this would also give us a very precious information of its origin. For instance, we know that stars are found surrounded by disks, and if we find disks similar to the ones we observe in stars surrounding these planets, this would give us hints that maybe these planets are formed similar to low mass stars. On the contrary, if we observe no disks, or we observe disks which are truncated or which have been reshaped in some kind of ways, then this would give us more indication that probably these planets were formed in planetary systems, and during the process of ejection from the planetary system, this could have undergone some traumatical process.
Well, I am, for one, am really looking forward to where this research goes. What is next for you personally right now?
Personally, I'm now working, for instance, in another related topic interesting for these planets, besides collaborating for the all I have mentioned. But I'm now trying to find precisely the age of these planets. We know that the region that we studied is very young, but has an age between 1 and 10 million years. And this is not precise enough for some kinds of studies. I mean, for instance, to the I explained that these planets fade very quickly with time, and this
Right.
is and then um, to precisely know the mass of this planet, we need to know precisely their age, and this is one project I have now ongoing. So a precise age for each planet would help us to better constrain the mass of those planets. which is also a very important parameter to study.
Well, thank you so much for being here and for answering my questions. I want you to come back when you have another paper out because I am fascinated by rogue planets, floating planets, and so I want to learn more as you learn it. So again, it has been great having you here today, Dr. Miret, and we will hopefully see you again.
Thank you very much for.
This has been The Daily Space. To all of you watching, the conversation ran longer than we can air here on Now Media. You can catch the interview in its entirety on our website, dailyspace.org.
While you're there, check out our show notes to find more information on all our stories, including images. As always, we're here thanks to the donations of people like you. If you like our content, please consider joining our Patreon at patreon.com/CosmoQuestX.